Welcome, everyone. I'm Edward Name. I'm the GM of Amazon FSx, and I'm here today with Daryl Osborne, who will be on stage in a little bit to do some demos and show you FSx for Lustre in action. We're really excited to be here today to talk to you about Amazon FSx for Lustre, which is a new service that was announced yesterday and launched yesterday during Andy Jassy's keynote. And in this session, I'm going to start with a very brief overview of AWS storage and the options available across our storage portfolio. I'm then going to talk to you about running compute-intensive workloads on AWS, because that's really the goal of FSx for Lustre, is to support compute-intensive workloads. We'll then introduce FSx for Lustre, why we built it, what it offers, and how it can help you run high-performance computing, machine learning, media processing, and other compute-intensive workloads. Daryl will then lead us through a part of the session that will show FSx in action. So he'll do some cool hands-on demos of using FSx, and he's going to demonstrate the performance that you can get from it. And then we'll save time at the end for Q&A. So let's get into it. And let's start with an overview of AWS's storage offerings. And the summary is, we have a rich set of storage offerings to support whatever workloads you want to run on AWS. We have object and archival storage, so S3 and S3 Glacier. We have locally attached storage, and that's EC2 instance local storage in EBS. And it's been an exciting week for our file offerings. We announced yesterday not only FSx for Lustre, but also another FSx file system, FSx for Windows File Server. And we also announced that EFS is getting a new infrequent access class of storage that's coming soon. We also have a wide set of data movement services for moving your data into AWS, out of AWS, and across services. And most of you are here because you're looking for storage to use with your compute-intensive workloads. So I want to talk a little bit about running compute-intensive workloads on AWS to tee up the discussion. And so let's start with a definition. What do we mean by a compute-intensive workload? Well, it's any workload that processes data at a rapid pace with lots of compute power. So another way to say it is a workload that processes large amounts of data with large amounts of compute. And typically in these compute-intensive workloads, you'll have really massive data sets and large clusters of compute, and you want to use the compute to process the data that's in the data sets. And commonly, you need to have a high-speed network between the storage and the compute. And AWS provides a wide breadth of services for these types of compute-intensive workloads, a bunch of compute services. We have services like EC2 Spot. We have automation and orchestration services like AWS Batch, which has been very popular with our HPC customers. We have a number of networking services. We actually announced EFA, network interface for compute instances this week. We also announced a C5N compute network optimized instance that gives you a 100 gigabit network. And we have a number of visualization services as well that customers are using to really do more with their data. And so what does the typical compute-intensive workload on AWS look like? So commonly what customers do is they store their data sets in S3, which provides highly durable, very cheap storage for large data sets, fully elastic. And then there's two ways of making that data available to compute clusters. So the first way is that you copy data to the EC2 instance storage or to EBS volumes attached to the EC2 instances that you're using in your compute cluster. The other way is that you copy data into some sort of self-managed high-performance shared file system, and then your compute cluster has access to the data on that file system. So those are the two common ways to work with your S3 data for compute workload. And then once your workload's complete, you write results back to S3. And sometimes you might do that at intermediate points to do some sort of checkpointing. And then when you're done, you'll delete the compute cluster and the local storage or the shared file system. So it's a very typical type of workflow. Now, you'll notice that I mentioned that for both options 1 and option 2, you're using a file system. You might be wondering why. Why do you need a file system? And it's either a file system that is local to the EBS volumes or to the EC2 local storage, or it's a file system that's a shared file system. Well, there's really three reasons. The first is latencies. So a lot of compute-intensive workloads are latency sensitive. And so you'll want to have the data on a file system that's local or on the local network close to your compute. The second are request costs. So for a lot of these workloads, if you're going back to S3, every time you want to read data, a lot of times you're reading the same data over and over again, you're paying request costs. And so those quickly add up for workloads that are processing a lot of data in a data set. And then finally, a lot of the applications that people are running to process their data require a file interface. So they're written for file system APIs, operating system APIs that provide file functionality. So that's generally why file system's involved in between your S3 and your compute. And so option 2, which I said is a shared file system, is great because it allows you to expose your data to your instances as local files, but you don't need to shard the data across instances and volumes like you do in option 1. It's just a shared file system that all of your compute instances can connect to and access the same set of data. But for a shared file system to work for most of these workloads, it needs to really provide two key things. First is a POSIX interface. So files and directories will appear and work just as they would on local storage, and all of the APIs that your operating system provides to work with a file system will work with it. So your applications will just work. And it needs to provide very high levels of throughput in IOPS while providing very low latencies. And the high levels of throughput in IOPS is because you have a lot of compute processing a lot of data. And so you need a lot of throughput, a lot of IOPS in aggregate. And most shared file systems that are deployed for these compute-intensive workloads are what we call parallel file systems. And so with a traditional file system, you'll have a single file server that all of your compute nodes connect to. And that ends up becoming a bottleneck, so you can't really get the high levels of throughput that you need for these workloads. And so parallel file systems exist to solve that problem. And what they do is they store data across multiple file servers to maximize the performance and reduce bottlenecks. So the way it works is you'll have your data spread across servers. Clients each individually talk to each data server. And there's a mapping that the clients are aware of for where data is whenever they need to request it. And so the bottlenecks that you get from everything going to a central server go away. And you also get low latencies because you have a single network hop between the client and the server. But it's really hard to run a parallel file system. It requires specialized expertise and lots of time. This is something that customers have been telling us over and over. They don't want to run and manage their own parallel file systems. They have to configure and maintain cumbersome software. There's a ton of performance parameters that generally need to be tuned. Nobody can just bring up a parallel file system and run it for their workload and it works. Like, it just doesn't happen. And then keeping it alive ends up being really challenging, especially as these things grow. When you have multiple servers and you have multiple disks attached to each server, it can become a full-time job just to keep a cluster alive. And so as a result, until today, high-performance parallel file systems have mostly been out of reach for all but the largest institutions and projects. So, and really it's out of reach unless you're lucky enough to have experts managing the file system for you. And most of these file systems are petabytes in size because what companies generally do is they build them for peak capacity across teams. And so now you're talking about clusters that are maybe tens or hundreds of servers with thousands or tens of thousands of disks. And so you're really talking about a very challenging thing to keep alive. And what customers have told us is that they have entire teams that are dedicated just to keep these parallel file systems alive. That's great if you have the luxury of having those teams available to do that. But for most projects, that's not a reality. And then it's not trivial to move data into and out of a parallel file system. We're talking about large amounts of data. So on AWS, for example, to move your data from S3 onto a parallel file system, and you want to do it fast, generally you're going to need to set up data management tools to move the data over. You're going to want to spread the movement of data across multiple nodes, across multiple threads. You're going to need to track what data is moved over and if it's successfully moved over. And all of this actually gates your being able to start processing your data. So there's a ton of complexity and a ton of time that introduces. And so based on feedback from customers about how to better enable compute-intense workloads, from a storage perspective, we thought, how can we do better? And that's what we set out to deliver with FSx for Lustre. And that's why we built it. And FSx for Lustre is a fully managed, high-performance parallel file system on AWS. It makes high-performance Lustre file systems accessible and simple for the first time. It seamlessly integrates with your existing data repositories, both S3 and on-prem data stores. And it's really easy to launch and run with virtually unlimited scale. And those are really our design goals for this. That's what we've delivered. So let me start with what is Lustre, because actually, show of hands, how many people are familiar with Lustre as a file system? Okay, so maybe about a third of the folks here. So it's one of the most popular parallel file systems. It's open source. It was started in 1999 at Carnegie Mellon University. And since then, it's matured into a file system that's heavily used by companies, by research institutions, by government agencies for a pretty broad set of use cases, including things like seismic processing, financial modeling, EDA. It's used across a really wide variety of use cases, and it's because of the performance that it delivers. In fact, 60% of the top 100 fastest supercomputers leverage Lustre for data storage. And again, for the most part, it's been out of reach for most people to be able to run a Lustre cluster. And with FSx for Lustre, there's really 6 key benefits that we're providing. And I'll go through each of these. But it's massively scalable performance, seamless access to your data repositories, so you can link your file system to your long-term data stores. It's simple and fully managed. It provides a native file system interface. It's cost optimized for compute-intensive workloads, and it's secure and compliant. So let me talk about each. So first, in terms of performance, the Lustre file system itself provides throughput of up to hundreds of gigabytes per second and millions of IOPS. And it provides consistent sub-millisecond latencies. And that's really due to 2 things. The first is the parallel architecture, where clients and servers are just one network hop away. And the second is that we're building this on SSD storage. And so you get the latency benefits of that. And it also supports hundreds of thousands of cores. So you can really have a really large compute clusters accessing data set. And with FSx for Lustre, we've designed it so the file system throughput and IOPS scale linearly with storage capacity. And that's generally because with the more data you have, the more you need aggregate access to that data. And so specifically, each terabyte of storage provides 200 megabytes per second of throughput. And that's 100% of the time you can get that 200 gigabytes per second of throughput. You may even see higher levels depending on your I/O pattern. And then, as I mentioned, file systems can scale to hundreds of gigabytes per second and millions of IOPS. So let me talk about how the S3 integration works, because I've alluded to it a couple times. So the way it works is you'll have your data stored in S3, like you do with a typical one of these compute-intensive workloads. And you'll create your file system. And when you create the file system, you link it to the S3 bucket where your data is. And as part of the creation of that file system, what we do is we build all of the file names and the directory names in your file system that map to what's in your bucket. So when you mount your file system for the first time, you're actually able to see a full directory structure with all your directories and files listed in your file system. And then when you access a file for the first time from the file system, it pulls the data in real time from S3. So we call that lazy loading the data from S3. And so what that allows you to do is, let's say that you have a really large bucket. You only need to use a subset of the data in that bucket. You don't have to move all of the data over, and you don't have to specify, here's the data that I need to move over. It just automatically moves when your application needs to access the data. And then there's also a API that's provided for you to push data back to S3. And we track what data has changed since your import from S3, and we only push the changes back. So it's only incremental changes, and it's actually incremental since the last time you ran that commit API. Now, if you have a workload where it's really latency sensitive for that first access, you can also do a batch load of your data from S3 onto the file system, and we provide a command for doing that as well. But I think for most folks, the lazy load is what will make the most sense. So just to be like super clear on this, so let me walk through an example. So let's say that you have your file system up, you had linked it to an S3 bucket, and you want to access file1.txt. And so what happens is your compute node tries to access it. Lustre, FSX for Lustre detects it's not on your file system. It goes to S3. It gets that file from S3, pulls it onto the file system, and delivers it to the compute node. And there's a bit of latency there because it's going to S3 to get your data. So now let's say that you want to access it again. Now this time it's already on the file system because it's been pulled, and so it just delivers it back to your compute node. And so you don't have the round trip to S3 with the latency that entails. And then we've optimized the performance of the movement from S3 back and forth to make it really fast. And so we're really doing a lot of parallel stuff to make the movement fast. So first of all, your FSX file system is spread. A lot of them are spread across multiple file servers and multiple disks, depending on the size of the file system. And we really leverage that parallelism to send parallel requests to S3. And then even from a single server, we're using multi-threading as well. So if you do want to do a batch load and you issue that command, we're going to be pushing it at pretty high throughput because of that parallelism. And that's important because a lot of times this is gating the start of your workload, the start of your compute, and you want the data to move as fast as possible to the file system. And then cloud bursting is also supported. So the scenario here is you have your data on-prem, and you want to spin up some compute on the cloud, burst to the cloud to process the data. And so what you would do is you would spin up a FSX for Lustre file system. You would mount it from an on-prem server over Direct Connect or over VPN. You would batch move the data into your Lustre file system. You'd spin up your compute cluster on AWS. You'd process the data, and then you'd move your data back. So that would be the path for cloud bursting. And so, as I mentioned, simple and fully managed. We provision and set up the file servers and storage volumes. We configure and maintain the Lustre software. And with those two, we're really putting the power of Lustre in the reach of everybody, fully managing it for you. It provides a POSIX interface, so works like any file system would with your Linux applications. You don't need to change your applications. It provides read after write and read after close consistency, which is really important when you're accessing data from multiple nodes and you want to have a guaranteed consistency model. And also supports file locking, also important when you have multiple compute nodes accessing a set of data. And it's secure and compliant. Data is automatically encrypted at rest, PCI DSS, ISO compliant, HIPAA eligible. You access your file system from your VPCs. You set up endpoints in your VPCs and you apply security groups to them, so kind of the typical VPC model. Admin API is controlled through IAM, and then monitoring and logging API calls are through CloudTrail. And we've really cost optimized it for compute-intensive workloads. So your data on your Lustre file system is not replicated. And the reason we're not replicating it is because it's designed for these workflows where you have your durable data somewhere, you spin up a file system that's around for hours, days, weeks, in some cases months. You can commit data back to S3 at any point, or back to your durable data stored at any point, and you spin down your file system when you're done. And by not replicating it, we have the benefit of lower cost for us, which we pass on as lower price for you. And we also have significant performance benefits by not replicating the data. So it's really optimized for these compute-intensive type workflows. And the price is 14 cents per gigabyte per month. An interesting way to think about that if you think about these as kind of ephemeral workloads, is 20 cents per terabyte per hour. And so if you have a few terabytes for a few hours, you can do the math, and it comes out to a few dollars for running these massively large file systems. So as an example, I think the billing is fairly straightforward, but I'll go through an example just to make it super clear. So let's say that you have a total data set of 250 terabytes of data, and this is in your S3 bucket. And you want to process 25 terabytes of that data every day. And you need to do it at something like 5 gigabytes per second, so you decide to use this Lustre file system. And you run it for 10 hours each day. So what would your bill look like? Well, again, it's 20 cents per terabyte per hour times the 25 terabytes per job. And every job is 10 hours. You have 30 of those a month. So you're talking about $1,500 a month of spend. That's in addition to the $5,700 on S3 for your full data set. So for most use cases, this is going to be a pretty small percentage of your overall storage bill. You'll have your larger data set in S3, and you'll be able to selectively process portions of it and pay a relatively small amount storage-wise for doing that. And I've mentioned a couple of these workloads, but high-performance computing, Lustre is basically the standard in the HPC space. Machine learning often has these large compute clusters, requires very high levels of throughput, parallel access. Media rendering and transcoding, those both tend to be throughput heavy and very latency sensitive. Processing big data. EDA is another use case that we expect to be very popular with this. And then there's a whole bunch of kind of financial analytics use cases, oil and gas, seismic processing. So pretty broad spectrum of lots of data, need to compute it, and I do that in kind of these workflows. And we announced the service yesterday, and it was available immediately. And it's in these 4 regions: US West Oregon, US East Northern Virginia, US East Ohio, and EU Ireland. And we will be rolling out to more regions pretty quickly. And let me just talk about FSx more broadly. So on Wednesday, we generally introduced the Amazon FSx family, and it provides fully managed third-party file systems that are optimized for a variety of different environments or different use cases. So the other one that we announced yesterday was a fully managed Windows file server, and so that's for kind of traditional Windows applications that need native Windows file storage. Makes it super easy to spin up and store your data on Windows file servers and not have to worry about managing those. So kind of the core goals of FSx is simple and fully managed. The native compatibility and features and performance of these third-party file systems. But we integrate them with AWS services to make them much more useful than they otherwise would be. And an example is what we're doing with S3 with Lustre. And then cost optimized for the use cases that they're targeting. So again, with Lustre, for example, with the non-replicated version of the product. So let me hand it over to Daryl now to share some more details about FSx for Lustre and show a demo.
Great. Thanks, Ed. Appreciate it. So, I think the best way to share more about how we've made Lustre file systems accessible, easy to launch, easy to run, and actually seamlessly integrated with existing data sets is to see it in action. So I'm going to go ahead and switch over to my laptop really quick. So what we're going to do, I have a CLI command here that I'm going to go ahead and copy into my terminal window. So as you can see, this is a very simple command. It's a create file system command. If you haven't downloaded the latest CLI, we made this push yesterday, so download the latest and you'll have access to the FSx API. We identify what type of file system it is. Again, as Ed mentioned, there's 2 different Amazon FSx file systems, one for Windows file server and one for Lustre. So we need to identify what type of file system. Then we also identify the storage capacity. So in this example, I'm going to have a 3,600 gigabyte file system that I'm going to create. I identify the subnet. This is the subnet where my file system is going to reside. Optionally, I am linking this to an S3 bucket, the NASA NEX bucket. This is an open data source bucket. We'll talk about it a little later. And that's it. That's really how simple it is. It is going to have the default VPC security group associated with it. If I wanted to add additional security groups, I could do that at this command as well. So we're going to go ahead and just run that. As you can see, within just a matter of seconds, the API is finished. And never has it been easier to launch a Lustre file system. It will take a few minutes for the file system to be created. Because I linked it with an S3 bucket, as Ed mentioned, we are going to load the object data, or not the data itself, but the metadata, the object name, and the structure of these objects into the file system, what we call a metadata load. And that's going to happen as a part of the file system creation. So earlier, I created a file system. It's a little larger than the 3,600 gigabyte file system here. But what I did was I also linked it to this bucket. And as we can see, once the file system is created and we start loading the object metadata into the file system, we can see the activity. So this is a CloudFormation template, or I used a CloudFormation template to launch a CloudWatch dashboard for my file system. The very top is the available storage. Next, we have the throughput in megabytes per second. Then finally, we have the operations per second. So as you can see, we loaded metadata for 373,000 objects. And that load took only 11 minutes. So we were getting roughly 567 objects per second. So very easy, fast to go ahead and load that, really associate it with an S3 bucket and load the metadata so we can have access to that metadata. So the data set that I'm using today is, it's in an open data repository on AWS. NEX, it's really a platform for scientific collaboration, knowledge sharing, and research of earth sciences. So it contains objects of different sizes and file types. We have NetCDF, or Network Common Data format files. They're really designed for storing multi-dimensional data. We have some TIFF files, and we have some HDF files. These are hierarchical data format, really designed to organize large amounts of data. We also have some PDFs and some text files. So they range from 4 kilobytes all the way up to hundreds and hundreds of megabytes. So what we're going to do is what I'm going to do is lazy load this data into my file system. And because FSX for Lustre is a POSIX-compliant file system, there's really nothing special I need to do. So what I'm going to do is just hop over. Everyone can see that. Great. I'm going to go back to my screen. Now here I just have a simple ls of a file. So this file is roughly, it's 181 megabytes. It's a TIFF file. It's sitting in, the metadata is on my Lustre file system, but the data still resides in Amazon S3. So up at the very top, I'm going to go ahead and just run nload, so we can monitor network traffic to this instance. So I'm going to simulate an application reading this file. So I'm actually going to just do a cat into tempfs. So I'm going to read all of the data of this file, and we're going to see what happens. So you notice I kicked it off, and it took roughly 4.2 seconds. But you notice for about the first 3.5 seconds, we didn't see any network traffic. Why? Why not? Well, at that time, the object data was being loaded from S3 into the FSX for Lustre file system. Once it was loaded to the file system, then at the very end, we loaded it into the client, and the client was able to get it. So if we read it again, how fast is that going to be? 0.116 seconds. Very fast. So where did I read this from? Cache. It's on my client cache. Okay, so I did not, as you look at the network traffic on my end load screen up above, you notice then when I did that cat, the subsequent cat, data was not loaded from the FSX file system. So what we want to do is we want to go ahead and flush, drop our cache. So it's not going to reside there. Now that we've dropped our cache, let's go ahead and run that again. And take a look at the end load output. So just a little bit. We loaded that now in 0.442 seconds. So it wasn't the 4 seconds that it took to load that data in from S3. We know that it loaded it from the FSX for Lustre file system because, again, it was very fast. And we know that that file actually resides on that file system. The data resides on that file system now. So let's go ahead and just take a look at where my file is. So if we do a df on my file system, if we scroll up, we can actually see that that 181 megabyte file is loaded on one of my OSTs, my object storage target of the Lustre file system. So that's where it resides. So I know that that data has been loaded, which is great. If we scroll up, we can actually see the metadata in the MDT. So we've got 4 gigs of metadata that describes all of those objects in the file system. So what if we wanted to recover that storage? 181 megabytes isn't much, but if you had a lot of data in there and you wanted to load more data, what could we do? So we could actually release that data from the file system so we can add more data in if we wanted to. So by issuing a simple HSM release command, we can release that file. Let's go back to the DF. We still see it hasn't been released yet. We issue it again. Now the file data is gone. So it's no longer in my FSX for Lustre file system. Upon the next read, what happens? We're going back out to S3. It's going to take 4.8 seconds. Again, we just see the network activity on this instance. Once it hits the FSX for Lustre file system, then it'll load that data into the client. We can do it again. We'll notice that we're reading from cache. We'll flush that cache. We'll read it one more time. And now we know that we're getting it from the Lustre file system. So a very easy way to bring data in. Now, this is simulating what your application would be doing. Upon first access, you will have higher latencies because, again, we need to go and retrieve that object from S3, load it in the file system, and then deliver it to the client. So sometimes your application, your workload may be sensitive to that latency. So maybe you want to load the data in a batch, sort of a batch format, as Ed mentioned. So we can do that as well. So I actually ran this earlier. Oh, well, actually, let me go back and describe to you what we just did. So again, upon first read of that file, it loads from S3 into the file system, and then it delivers it to the client. In my example that I recorded, it was 4.293 seconds. So my next read, where did it come from? Cache. Very fast, 0.109 seconds. I dropped my cache, then I read it again. Fast, still fast, but this time it came from FSX, and it was, in my example, it was 0.396 seconds that I ran a little earlier. So again, very fast access to your file system, and it allows you to get high levels of operations per second and high levels of throughput. So when we talk about batch loading files, you can issue a single command like this, basically identifying all of the files in your file system, then issuing this HSM restore command for all of those. So by using a simple command like this, you're able to do these batch loads. And this is really what it looks like. Again, the client itself none of the data is passing through the client. It's going directly from the S3 bucket to the FSX for FSX for Lustre file system. And it's not going through a specific node. The way that Lustre works is all of the OSTs that we have, and you saw the list of my OSTs, those are actually getting the data directly from S3. So it's highly parallel. So that's how we're able to deliver high levels of throughput and operations per second as a part of this load process. So with my first example, you see here that is the metadata load of the file system. And then what I did was I did a batch load to load all the data in this file system as well. As you can see, the amount of throughput and operations per second basically dwarfed what that metadata load was. You can barely even see it on the bottom chart, which is the operations per second. So we have 373,572 files. It took 32 minutes to load this data. So we were able to achieve 15.8 gigabytes per second at our peak. We hit a peak of 528,000 operations per second. And as a part of this process, we loaded 22.7 terabytes of data. So again, very fast. I didn't have to spin up a fleet of EC2 instances to ingest that data. I could have a simple EC2 instance, issue a simple command, and then all of the work is done by Amazon FSX for Lustre as we import all that data into the file system. So you'll also have workloads where you'll need to generate lots amount of data as well. TIFF, it could be terabytes of data, it could be petabytes of data, but you're going to have lots of, an opportunity to ingest and generate lots of data. So in the same example, I have my file system. It's a 108 terabyte file system. So if you do the math with 200 megabytes per second per terabyte of storage capacity that I provisioned, we should be able to achieve very high levels of throughput. So during my ingest of data that I generated from a fleet of these EC2 instances, we can see that we're able to achieve high levels of throughput, even well above the throughput that we achieved when we were importing the data directly from S3. So I generated 6.4 terabytes of data. It only took 4.5 minutes. And it was roughly, at peak there, we were getting around 23.9 gigabytes per second. And I think at the size of my file system, I should have been getting 23.12 or something like that. So slightly higher than what the throughput capacity should be based on the metrics of 200 megabytes per second per terabyte of data stored. So as Ed mentioned, we just launched this yesterday. We were very excited about it. We do have a video and some blog posts about the service. We are going to be having white papers and reference architectures around how to use FSx for Lustre. Our documentation is out there as well. So the commands that you saw me run today, those are available in our user guide. And we encourage you to go out, take a look at it, and test it out. We do want to thank you. We do have time for Q&A. So what I'd like to do is open it up to the floor so that you can ask questions. Before everyone leaves, though, do complete the surveys of the session so we can gather feedback from you, so we'll be able to improve our sessions year over year. Question?
So are you using standard Lustre distro?
On the client side or on the server side? Okay.
Yeah, so this is a standard version of Lustre server and client. So it's kind of, if you've used Lustre before, it's the same type of performance, the same functionality that you would get from a typical. Yep. Yep. So it's the latest stable version of it.
Yep. Question up here.
I got two questions. One is what happens if the bucket size is a lot larger than the provision capacity of the license? And
We'll start with that. OK, so the question is, what happens when the bucket size, and it could be a bucket or even a prefix inside that bucket as well. So you could reduce it to a smaller set of objects. So what happens if the S3 bucket or the prefix is much larger than your file system? And in every case, you may want to have an environment like that because you have a large data set. You don't need to process all that data. So what's going to happen is it's going to load, it's going to fill up your file system, and then it's not going to load any more data in there. So what you'd have to do is release the files, the data of those files from your file system in order to ingest more.
And one thing to clarify, if you're linking your file system to your bucket, it only, when you first do that link, it only brings in the file names and the directory entries. So you could have like a multi-petabyte bucket, spin up a 5 terabyte Lustre file system. You're not going to consume the full bucket unless you start pulling data in. And so it's really, if you're pulling data in and you end up filling up your file system, you can release data back to the S3 bucket.
Yeah. Great. Question back there. So the question is, do you need to do that by hand, or is there some type of caching mechanism?
Cache eviction.
Oh, cache eviction. Do you want to cover that?
So yeah, you would do it by hand. You'd use the command that we provide, but it's not a cache eviction type of mechanism.
So the command that you saw me run earlier, the HSM release, so basically we release that data, and we saw it actually be removed from that OST, and then you could import that in. So you could do it individually, or you can actually run a similar batch command. Instead of batch loading data, you can batch evict data as well by however you want to sort of define that find or search criteria. Down here. So the first question was around permissions of your objects, okay? And the second question was around soft links. What happens when you have soft links? Okay.
So for the permissions, right now when we push the incremental changes back to S3, we're not maintaining the permissions in the object. We've gotten some feedback from customers this week that would be useful, so we're looking at doing that. And we can basically just store it as metadata in your S3 object. So it would be good to understand the use case that you have in a little more detail to understand what the need is, but we're hearing that, so we'll try to respond quickly to that one. What was the second one, sorry? Do we support soft links? Yes. Yep.
Back there. So the question is, how frequent do you sync back to S3? So that's a manual command that you would issue. So you would actually issue a command to write that file back to S3 as an object. And it is incremental as well.
It's incremental, yeah. And we actually originally we were planning to automatically sync data back, and we talked to customers about that, and they said actually don't do that because we don't want to keep sending data back and wait for that and pay the request costs. We'd rather batch do it, and so it's really giving you the command to do that, and we detect what the incremental changes were.
Great. Let's come over here.
According to Mr. Torvalds, Lustre support is going to be brought to Linux kernel starting around 4.18. This is what I read in the journal. What exactly does it mean for this solution?
So the question is, Linux is going to be dropping Lustre support from starting at Linux kernel 4.18. What does that mean for our service, basically for FSX for Lustre?
So I would say that we're committed to keeping Lustre going forward, and so we're going to continue to work with the community and invest in making sure that it's available.
Right. Absolutely. Good. Right here. So 2 questions. What happens when the file system is full? Do you need to evict objects? Do you have to manually purge it or automatically? So you would have to manually release the file data from your file system in order to recover more data, to load in more data. Yep. And your last question? Is it possible to resize the file system? So today it is not possible to resize the file system. When you create your file system, you identify the storage capacity, and then we launch that Lustre cluster to support that size.
And the part of the reason for that is because we really do see this as, kind of for shorter term. Like it's not going to be, you're going to have this single thing around for years, and you need to scale it. So. But again, this feedback, if people feel that's important, it's good feedback for us.
Yeah, really within minutes, you can have a tens of terabytes, hundreds of terabytes Lustre file system. Use it for a couple of hours, maybe a day or so, tear it back down. If you have more data, spin it back up again. We have per second pricing, billing.
Yep.
Per second billing on the amount of data that that you created as a part of your file system. So yeah, I really think of it as more of a on-demand scratch file system for compute-intensive workloads. I don't see it sticking around for a long time. Right here.
What if you have multi-terabyte S3 object? Does it pull the whole file down and you only portions of it?
So the question is, what happens if you have multi-terabyte objects? Does it pull down the entire object when you do the read?
Yeah, the answer is yes, it does. We're looking at an optimization where we would, support some form of byte range, pulling portions down. But for now, it does pull the full object. Yep.
Great. Right here.
At the moment, we are running multi-petabyte platform with Dell EMC Isolon from Dell EMC Isolon platform in our data center. Is there an opportunity to link this to a cluster system while we have already been cloud enabled? Is there somehow a linkage?
Sure. Okay, so the question is, they have an on-prem Lustre cluster. Is it no? It's just an on-prem data set? An EMC Isolon on-prem appliance. They have all their data, petabytes and petabytes of data. They want to go and see if they can link that data repository to an Amazon FSX for Lustre file system.
So the way that you would connect the two is over a direct connect connection, you would have your on-prem file system mounted to a server or several servers, and you would mount your Lustre file system to the same set of servers, and then you'd be able to copy data between the two. So that's what the solution would be. It would be more of a manual process than our S3 integration, but it is doable in that way.
Right back there. Okay. The question is it possible to have intersect clients or connections between the clients and the resources that support the FSX for Lustre file system?
I don't believe so. We can check, but I don't believe so. But that's also good feedback if that's a requirement.
Question right here. The question is, can you have multiple file systems or objects linked to the same bucket?
Yes. Yep. If you're writing to the same objects, you're saying from both file systems. So the way that it works is we actually, when you call the when you commit the data back to S3, we actually write it to a separate prefix. We kind of maintain the same prefix structure within that separate prefix, but we write the incremental results back there so that you can then decide if you want to kind of batch move it back to your original objects or not. So it avoids the conflicts that you would be thinking about. No, you can't. No.
Right here.
You mentioned the notion of kind of a dynamic scratch base, and it seems like one of the challenges there is the cold start time. So I think in one of the slides it was like 32 minutes to do hundreds of thousands of objects and reading that metadata. What are you guys doing to sort of address that challenge? Either having it sit around for longer or deal with the cold start problem?
Yep.
So the question is, during the data load of objects, there is higher latency when we're actually ingesting this data from the S3 bucket. What are we doing to address that to try to improve the performance?
So a couple things. So during the initial creation, again, the data is not moved over. It's just think about it as the file system metadata. And if you have, I forget exactly how many objects you...
Yeah, we had 373,572 objects, which consumed about 22.7 terabytes of data.
Okay, so so a couple options. So the first is you can actually link your file system to a specific prefix within your bucket, so you don't have to wait for like everything to load. And the second is, if lazy loading is an option, if the latencies are tolerable, then that's a path where you don't need to wait for your full data set to move over in order to start processing. And you can do the lazy load for portions of your data set as well. It doesn't need to be for the full.
Time is a function of the number of files, not necessarily size.
It's the number. The initial time for building the metadata is all about the number of files, not the size of the files.
Yeah. Yeah, but you can really go from, when I did my test, I had some minutes in between the metadata load and then the actual data load. But when really you add it up, around 11 minutes to create the hardware or provision the resources to support the file system, another 11 minutes to actually move that metadata in from my 373,000 files, and then another 32 minutes to ingest. So you're you're under an hour to ingest 22.7 terabytes of data from S3 with literally 2 commands, a create file system command and a batch load command. Right here.
Do you pay for it while it's loading metadata? Or is it only after the metadata is loaded in?
Okay. So the question is, when you start being charged, are you charged for the metadata load or once the data has already been pulled in? So you're charged by the amount of data you provision for your file system. You set that when you create the file system. You identify a storage capacity. And that's when, as we're building the resources out, you will be billed when it's available, or when it's started.
Yeah. So think of it as there's kind of 2 things that are happening. The first is we're provisioning the file system for you. Once it's provisioned, you do start getting billed, and then we start moving the metadata in. Usually that's a couple minutes, if not less. So, but you are getting billed during that time period.
Question back there. The question is, are there any plans to integrate this with EMR for big data movers?
I'd love to hear kind of the scenario that you see this being useful for, like within that.
So the EMR FS doesn't cut it because the EMR on the local disk, you know, you can't compare it with the EMR disk goes down with the EMR FS. But this would actually solve it.
Okay. So it's good if we can actually, if you have time, a few minutes after, I'd love to talk a little bit more with you about that in detail.
It's back there.
Good idea.
So the question is the S3 syncing a standard S3 API operation?
Yeah. Okay. So it's the standard limits that you have for your bucket and for operations associated with your bucket.
Yeah. But you don't issue that. That's a part of the FSX for Lustre service. We'll do that. You issue the command to ingest that data in, and then FSX for Lustre does the magic for us. All of those parallel get object API calls.
Do you see that as a challenge, or? Okay, just curious. Okay. Yeah.
Okay.
Yep. Okay.
Question back there. The question is, can you link multiple S3 buckets to the single file system?
So the answer is no, and that's really because we're aiming to do this kind of one-to-one mapping of your kind of prefixes and your set of objects to the file system metadata. So for the direct linking, it's to a single bucket. However, if you have data in multiple buckets that you want on the same file system, you can get the data from your S3. You can just make get calls from your client that has the file system mounted, get the objects, and write them to the file system. So it's a standard file system, and you can just get data from other buckets in kind of that way. But the direct linking is a one-to-one.
Okay. Question here.
As FSX for Lustre evolves, are there plans to have policy-based queuing to objects from Lustre?
So the question is, as FSX for Lustre evolves, are we going to have policy tiering as a part of it?
And what kind of policies would you see as useful?
For customers that need to always have the Lustre file system available, based on duration, access time, queuing off, without having to manually run commands every time.
I see.
So basically pin objects or pin files so that it won't be released, and just keep it there?
Both ways, to keep objects always in the Lustre file system,
Okay.
and also the files that are not used based on access time, to be able to push it off the object.
Evict them.
We don't want to minimize the utilization on that.
Okay, that's a good idea. Okay, thanks. That's good feedback.
Yeah, that is good. Question back there. So the question is, how does it scale when you have lots of clients accessing the same file?
So there's a couple ways to think about that. Lustre provides options for you to specify at the file level how you stripe your file across multiple disks. And so if you have, let's say, a sizable file, and you know that there's going to be a bunch of clients accessing different portions of that file, you can stripe it across the multiple disks, and that's going to reduce the contention that you have on that file. If they're all hitting like exactly the same, same set of bytes all at exactly the same time, I mean, there's just laws of physics in terms of, being able to serve that. But Lustre really is designed for kind of this like high concurrent access to single files by supporting the striping. So I think most people would say that it does a really good job of supporting that type of access.
Great. We have 1 minute left, so maybe 2 more questions, these 2 questions, and we'll finish it. Right here.
What happens if an object is already in the Lustre cache? Will be modified out cache or something else? So it will change the back.
You mean if it's a new version? Oh, sorry, go ahead. Repeat that question.
Sure. So the question is, what happens if you have an S3 bucket linked to a file system. The object, you imported the data is actually in the file system. You make a change to that object. What happens in that scenario? You've got an object that has the latest data. Your file system has, in a sense, stale data because it's not the same version of the object as you have in your bucket.
Yeah, so if the object has already been pulled in, then it's already on the file system. So if you have a new version of the object, you would need to, and you wanted to pull that in, you would delete the file from the Lustre file system and do a read again of the object, and it would pull the latest.
Okay. One last question. So does it support memory map operations?
I believe so, but I'd have to check. I don't know 100%. Yeah. So it'll load the full file from S3. So that's how it works. Yeah, it's an optimization we're thinking about. Yep.
Yeah. All right. Well, thank you so much for your attendance and for all the great questions.
Thank you, guys.
Have a great day.